Welcome to this explainer. Today, we're going to move past all the modern hype and magic to see how centuries of thought, mathematics, and human imagination actually built the artificial intelligence tools that are completely transforming our world today. We hear a ton about chatbots and self-driving cars, right? But to truly understand these tools, we first need to figure out exactly where they came from.
So, let's dive right in. To really wrap our heads around artificial intelligence, we have to recognize that it's absolutely not magic just appearing out of thin air. It is actually the combination of historical math, massive amounts of data, and modern computing power. It's a long, fascinating journey built by philosophers, neuroscientists, and engineers over literally hundreds of years.
Section 1. The roots before computers. Long before ChatGPT was even a blink in a developer's eye, and honestly way before computers were even a thing, the foundational ideas of artificial intelligence were being mapped out by brilliant visionaries using nothing more than pen and paper. Think about it. Starting way back in the 1700s, we have Thomas Bayes updating probabilities based on new evidence. That's an idea we still use in today's spam filters. Then, in the 1800s, George Boole creates yes or no logic, proving logic could be represented mathematically with trues and falses or ones and zeros. And right around that same time, the incredible Ada Lovelace imagined that machines could manipulate abstract symbols, not just do basic arithmetic. They were laying the absolute groundwork for programmable intelligence. Moving on to Section 2, mimicking the biological brain. Eventually, the conversation shifted. Scientists began looking inward to our own biology, asking this totally wild question: could we create a mathematical version of the human brain's billions of firing neurons? Well, that brings us to 1943, when Warren McCulloch and Walter Pitt proposed the very first artificial neuron. Imagine a super simple decision box. It receives signals, and if the total incoming signal is strong enough, it crosses a threshold and says yes. If not, it says no. It sounds incredibly simple, but it was a massive first step toward what we now call neural networks. And this leads us perfectly to the philosophical leap taken by Alan Turing in 1950. He asked the ultimate provocative question: can machines think? But instead of just debating it over dinner, he proposed the imitation game, which you probably know today as the Turing test. Turing argued that if a human messaging with a machine cannot tell if they're talking to a computer or another human, well, that machine is showing genuine, intelligent behavior. He basically turned a sci-fi dream into a serious scientific question. Which brings us to Section 3, the birth of a research field. This dream of thinking machines officially became a formal research field in 1956 at the famous Dartmouth Summer Research Project. Heavyweights like John McCarthy and Marvin Minsky got together, completely believing that human learning could be described so precisely that a machine could simulate it. And shortly after that, Frank Rosenblatt developed the perceptron. This was huge. It proved a machine could actually learn simple patterns, like separating a picture of a circle from a picture of a square, just by adjusting its own internal weights based on examples. But there was a catch. It really struggled with complex patterns, and frankly, the computers back then just weren't strong enough to handle it. Next up, Section 4, the roller coaster, expert systems, and AI winters.
Because of those hardware limitations, progress definitely wasn't a straight line. Throughout the 70s and 80s, the field pivoted to rely on what they called expert systems. These were programs where humans had to manually write down every single logical rule. Like, if the patient has a fever, then suggest this illness. But as you can imagine, humans couldn't possibly write enough rules for every single complex real-world scenario. So progress stalled out. Expectations were sky high, but the tech just couldn't deliver, plunging the whole field into freezing periods of lost funding and zero excitement, known as AI winters.
That leads us to Section 5, the paradigm shift, machine learning. To thaw out of those winters and make machines truly capable, the entire field needed a massive reboot, a complete paradigm shift in how we told computers what to do. Basically, we had to stop giving them the rules. Look at it this way. In traditional programming, humans write the rules, the computer follows them and spits out an output. But with machine learning, the human just gives the computer data. We give it thousands of spam and non-spam emails, and we let the computer figure out the underlying patterns itself to make its own predictions. It was a total game changer. All right, Section 6, deep learning and modern neural networks. Fast forward a bit, and thanks to the internet giving us an absolute explosion of massive data paired with incredibly powerful GPU computer chips, this learning method evolved into something way more powerful: deep learning. By stacking neural networks into many, many layers, deep learning systems can process crazy complexity step by step. Take face recognition, for example. The first layer just looks for simple edges. The second layer builds those edges into shapes. The third finds specific features, like an eye or a nose. And finally, the last layer brings the whole shebang together to recognize a complete human face. Let's look at Section 7, how a neural network actually learns. But how exactly does it get so insanely accurate? To understand that, it really helps to think of the neural network as a highly dedicated student learning from their mistakes. It almost never gets it right the first time. It actually works in a continuous loop. The data goes in, the model makes a guess, then it checks that prediction against the correct answer and calculates its error. Finally, it goes back into itself and adjusts its internal weights so it can do slightly better next time. And it repeats this loop thousands, even millions of times. And because it learns entirely from these historical examples, the data we feed the system is absolutely everything. Quality matters for sure. Good data makes for incredibly useful AI. But if we train it on skewed or biased data, well, the system is just going to learn those exact flaws and make harmful mistakes. At the end of the day, a mathematical model is truly only as good as what we teach it. Okay, let's zoom out for Section 8, mapping the modern AI universe. With all this historical and technical foundation laid out, let's clear up that confusing soup of jargon we hear in the news every day. Think of artificial intelligence as the giant umbrella. Tucked inside that is machine learning, where machines learn from data. Inside that is deep learning, using those multi-layered neural networks we just talked about. Down from there is generative AI, like ChatGPT or those crazy image generators, which uses deep learning to create brand new content. And finally, sitting way on the outside of today's tech is AGI, or artificial general intelligence. That's the futuristic sci-fi goal where an AI could reason just like a human across any subject. And to be clear, we are absolutely not there yet. Finally, Section 9. The future is now, changing lives. But hey, even without AGI, the narrow AI we have today is powerful enough to be a vital tool. It has firmly stepped out of historical research labs and is actively changing how we live and work on a daily basis. In healthcare, it's helping doctors spot diseases much earlier in medical scans. In agriculture, we've got drones with AI flying over fields detecting crop disease and water stress. In governance, it's crunching data to monitor public projects and catch corruption. And in education, it's acting as a personalized tutor for students who just need a little extra help. But here's the catch. As we weave this incredibly powerful tech into the fabric of our society, we have to wield it wisely. To get the best results, we absolutely need systems that are transparent and secure. We have to constantly fight to improve data quality, to reduce bias. And ultimately, we need to ensure that these tools are designed to support and elevate human productivity, rather than blindly trying to replace it. We've traced centuries of math, logic, and computing that brought us to this amazing moment in history. But you know what? The most important variable moving forward isn't the algorithm, it's you. Now that you understand the history of this technology and exactly how these machines learn, how will you use them to shape the future?